Kia ora koutou. In this video, I'm going to try and get through all 3 of the excellence questions in last year's complex numbers paper. And I'm assuming when I'm doing this that you're pretty confident with the skills up to a fairly solid merit level. So I'm not going to go all of that slowly. Hope that's okay. If you're in my class and you've got questions on any of it, please just send me an email. So the first question is a locus question. And we just need to read really carefully, first of all, what we've got. Well, we've got this complex number here, and we're told that the real part of this thing is 0 and that z can't be -4, right? So that's so that we have something that's non-zero in the denominator of a fraction. And we have to prove that the locus of points described by z is given by this thing here. So the pretty obvious starting place here is to let z equals x plus iy. And as you know, if you're doing this for level 3 NCEA, that's a pretty good starting point with a locus problem. You can't just do it using geometry. So you need to make sure that you fully work it through. There are some ways that you could do this using geometry that some of us have looked at if you're in my 13 MCA class, but don't use them here. Okay, so we start off, let z equal x plus iy, and we just substitute that in. So on the left-hand side, we've got x plus iy minus 2i over x plus iy minus 4. Before I do anything, I'm going to look at that denominator and I'm just going to regroup it with the real part and the imaginary part. And up here, I'm going to do the same thing with the numerator because we know that we need to do that for what's coming next. So we start off like that, and now I multiply through the conjugate by the conjugate. So x minus 4 minus iy times x minus 4 minus iy up here. It's a proof question, so I'm going to be pretty careful to show that I know what I'm doing. And that means that in the denominator, when we multiply this out, we're going to have x minus 4 squared. This and this are going to simplify away with this, but I'm going to show that step. So I've got plus iy times x minus 4 minus iy times x minus 4. And then I've got minus I squared y squared. Now, working on the numerator, we get x times x minus 4 here, plus I times y minus 2 times x minus 4, minus iyx, and then minus I squared y times y minus 2. And we know we're going to clean up those I squareds, but I think it's worthwhile to show every step so that your working is really, really easy to follow. So in here, obviously, these disappear, and I squared is equal to -1. So in the denominator, we've got x minus 4 squared plus y squared. And up here, I'm going to reorder it with my real stuff first. So x times x minus 4. This is a real term, and it's plus y times y minus 2. And then I'm going to collect up the imaginary part together. So we'll just factorize the I out here. So we've got I times, let's see, xy minus 2x plus 4y plus 8 minus xy. So we've got that far. And now we have to look back at the question to go any further, right? So remember the question told me somewhere up here that the real part of this thing is 0. So the real part of that complex number is 0, which means that x times x minus 4 plus y times y minus 2 over this is equal to 0. And we know that the modulus is not equal to 4, so that means that the bottom line is non-zero, which means that we can multiply both sides through by it. So we're just working with this now. X times x minus 4 plus y times y minus 2 is equal to 0. And we've got to get that into the equation for a circle. So the first thing I'll do here is I'll expand it, and then I'm going to do completing the square as follows. Right, if you're rusty on completing the square, you really have to have that skill down fluently for everything in level 3 complex numbers. So there's a level 2 video that I've done on that one that you can watch. But the basic idea is we take those two terms, whack a box around it, we're going to halve this, and then we're going to take out the extra bit that we've added in. Same thing here. So this becomes y minus 1 squared minus 1. So we're nearly there. we've got to get it to the equation of a circle as given. So that's that first one done. All right, on to question 2E. So in this one, we've got to find the value of z. Right, z is a complex number, and we've got this condition to do with the moduli. So one thing just to think about, what are we trying to end up with here? Well, z is a complex number, so z is equal to x plus iy. We're not looking for the x and the y in here. We're looking for the modulus of z. And the modulus of z is just x, the square root of x squared plus y squared. So that's what I'm kind of hunting for. I'm going to start off again by substituting in z equals x plus iy. Right, so x plus iy plus 16 is equal to 4 times x plus iy plus 1, right? Because we started with this condition. I'm going to group real and imaginary terms, sorry, thinking about economics. So we'll just do that step first. Now I'm going to find the modulus of each side, which is this. So I'm going pretty slowly on this bit because there's a really common mistake that I'm hoping none of you have made, which is that in the next line I'm going to square both sides, right? So I get x plus 16 squared plus y squared is equal to 16 times x plus 1 squared plus y squared. Now, a couple of things that go wrong in these questions are that often students will jump from here. So you've grouped it up, and then you go, oh, yep, I'm going to end up squaring two sides. But what you can very easily forget to do is to square that 4. So I think it's worth just slowing down to make sure that you write the modulus line out first, and then you're more likely to see that you need to square both sides. So now the obvious next thing to do is just to expand everything out. But remember that what we're looking for here is not x plus iy. We're not ending up with a value for z. We're looking for the modulus of z, which is x squared plus y squared. And you can see a whole bunch of square terms in here, so hopefully something good is going to happen with those. X squared plus 32x plus 16 squared, which is 256, plus y squared is equal to 16 times x squared plus 2x plus 1 plus y squared. So let's expand all of that out. On this side, we're going to have 16x squared plus 32x plus 16 plus y squared. And the left-hand side hasn't changed. So hopefully you can see something cool happening here. We've got the 32x on both sides, so that can be subtracted. And now we've got, washing everything to the right-hand side, 0 is equal to, oh, well, I could do it a couple of ways. So I've got 15x squared here, and I'm going to have, I've lost a 16 in here. Just a second. Yep, that line before, I've got 16 plus 16y squared here. Right, so x squared terms first are done. These have gone, the x's, and now I've got 256 here and 16 here. So minus 240. But you can see where this is going. I actually want to leave that number there, but I'm not going to redo the video. And here I've got plus 15y squared. Right, so we're just about there. 240 is equal to 15 times x squared plus y squared. So what does that give us? 16 is equal to x squared plus y squared, which is the modulus squared. So 16 is the modulus squared, so the modulus will be 4. Now the modulus has to be a positive number, right? Because remember what it is, it's wherever that complex number is, it's the length of the line joining the origin and the complex number. So I think I really like that excellence question. It's a little bit different, but it's actually, it's not that difficult. But what it relies on is that you really have read the question and seen what you're being asked for. I'm betting there are a lot of students who got partway through here and just didn't really know where you were going. So just be careful to look at the start exactly what are you aiming to find at the end. Now the last question is probably the trickiest of the three, but It's not too bad. We're going to solve this equation here. And so again, we're going to start by let z equal x plus iy. We're going to substitute, and we're going to hope that a bunch of stuff vanishes. So thinking about what we've got here, we know that the modulus of z is equal to this. And we know that the modulus of z squared is equal to x squared plus y squared. So the original equation that we're working on is this here. Z squared is equal to I times the modulus squared minus 4. So we've done that little bit of work at the start. We can start subbing things in. So x plus I squared is equal to I times x squared plus y squared minus 4. We're going to expand everything out, and we're going to gather up the real part and the imaginary part. So x squared plus 2xyi minus y squared is equal to x squared I plus y squared I minus 4. I'm going to gather all of that up on the left-hand side. So x squared minus y squared, sorry, there's a 4i there. Right, x squared minus y squared, that's the only real bit. And then I've got plus I times 2xy plus 4 from here, minus x squared here, minus y squared, and that equals 0. But remember that 0 in a complex number means 0 plus 0i. So we've got two equations to solve. The real bit has to equal 0, and the imaginary bit has to equal 0. So x squared minus y squared equals 0, and 2xy plus 4 minus x squared minus y squared has to equal 0. So x squared minus y squared equals 0 gives me the condition that x squared has to equal y squared. If you think about it for a minute, what that means is that y can be either x or y equals negative x. We're going to have to look at both of those options. Right? So now we're going to take those and we're going to substitute them back into here. So if y equals x, we get 2x squared plus 4 minus x squared minus x squared is equal to 0, which gives me 4 is equal to 0, so no solutions. So instead we're now going to work with x, negative x equals y. So 2x times negative x plus 4 minus x squared minus negative x squared is equal to 0. Negative 2x squared plus 4 minus x squared equals 0. 4x squared equals 4. X squared is 1, so x is equal to plus or minus 1, which means that y is equal to negative or positive 1. So the two numbers are z is equal to 1, and then y is negative 1, so 1 minus I, or z equals negative 1 plus I. So those are the two solutions to that equation. Thanks for watching. I will do some of the easier stuff in that paper over the weekend.